Okay, hello everyone. Welcome to our signal system class. So last few days we have been talking about Fourier series mainly, where we dealt with periodic signals, right? And we also saw some examples and some filter applications and so on and so forth, where some periodic signals are used in in to drive some chips or some circuits or some such, and we saw what are the effects of different harmonics and how to reduce those harmonics or how to filter out a particular component out of a signal and so on and so forth. There are lots and lots of applications of Fourier series, and we explored a very little bit of that, right? So today our main agenda is going to be how we move on from Fourier series to Fourier transform, or let's talk about the transformation later. Let's see what this is all about, right? So far what we have been talking about were mostly in case of periodic signals, right? So periodic signals, we saw that okay, it could be a signal like this bipolar square wave, where the wave, it has a certain periodicity, right? So the most of the signals or the waveforms that we dealt with so far were periodic in nature, so they got repeated after some interval of time. So if this is the time axis, then this got repeated after every t seconds, say, right? Then that too would be the time period, and most of the things in the Fourier series were set by this time period, right? The fundamental frequency, which was 1 by t, then there were harmonics of that, right? So the basic principle was, whatever your time period is, whatever your repetition factor of your signal is, if you call it t, then there would be a fundamental frequency f naught, which would be given by 1 by t. What does it mean? It means that the signal, the spectral components that we many times saw, the discrete spectral components, amplitude and phase spectra, the amplitude spectra or the phase spectra, it will have a fundamental frequency of f naught, and then there might be, depending on the, of course, the symmetry, there might be a second harmonic or a third harmonic or a fourth harmonic and so on and so forth. But these things, they were discrete in nature, right? So only n equal to 1, then 2, then 3, then 4, 5, 6, so on and so forth, only discrete integer multiples of the fundamental frequencies were possible, right? So whatever spectrum for this signal you plotted, it could have a DC, and then you could say f naught, and then you could say the twice f naught, and so on and so forth, and bunch of these harmonics could be zero also, depending on the uh, you know depending on the symmetries of the signal itself, right? And there could be a negative frequency notion also if your series is of complex exponential nature. But if you use the trigonometric form, then there would not be any negative frequency notion, because we cleared that part, I think. Okay, so now the question is, what happens if the time period of the signal changes? You could say, okay, if the time period changes, then the fundamental frequency will change 1 by f 1 by t, and then the harmonics would change. But am I going to have, anything other than n equal to 0, 1, 2, 3, 4, 5, and so on and so forth? No, we are always going to get n equal to 0, then 1, 2, 3, so on and so forth. But the main change that we are going to observe are in terms of the frequency, not the harmonic numbers. We shall see shortly what I mean by this. Okay, so to do that, we have to take an example first. Let's take the example, a very simple example of a unipolar square wave. Okay, let's plot it like this. So it is on, and then for some time it is off, and then it is on again, and this gets repeated. So this is a periodic signal of a period, time period capital T. Let's call this the t by 2, let's call this the minus t by 2. So this is the overall time period of the signal, and in this time period of the signal, it is on only for a certain amount of time. So minus a by 2 to a by 2, I have my signal, maybe plus v volts, and outside this, from a by 2 to t by 2 and minus t by 2 to a by 2, it is 0. So we can write it like that. I am not going to do that because I hope you understand the nature of the waveform that we are going to take, right? So this is the time period, and this is the on time of my signal, right? Sorry, this is the on time of my signal. Great. Now what we are going to do, let's call this signal our ft, or rather let's call it fpt. because this is a periodic signal of periodicity t. So you can readily find out what the fundamental frequency should be. It should be 1 by t, right? That's great, because we don't need that. Fine. Now what we are going to do, we are going to try to find the Fourier series, the exponential, complex exponential Fourier series. We are mostly interested in the coefficients only. So the series would be written as, if you remember, I'll keep on writing this. So the series would be written as an infinite sum, where n sums from minus infinity to infinity, of course, and then we write the coefficient. Let's call them Cn, okay, or we can call them Cn ripple, because this is the complex exponential form, and then e power j n omega naught t, right? Omega naught, you understand, it is twice pi f naught, right? Great. So now this is my Fourier series, and you can readily see that we are doing exactly what I said just now, that I have discrete number of coefficients, and as n varies from 1 2 3 4 5, we are basically having 1 omega naught, then twice omega naught, then thrice omega naught, 5 omega naught, 6 omega naught, so on and so forth. So those are your fundamental frequency and the harmonics, right? Great. So now we calculate, we also know the formula for Cn ripple, because we have seen this. It should be 1 by t. Then we do an integration over one time period. We can take the time period to be anything. We can take it from 0 to t, but in this case, because it will make our life easier, we are going to take minus t by 2 to t by 2, right? And then we integrate our function ft, or better call it fpt, multiplied by e power minus, we have all done this bunch of times, and we integrate in time. Wonderful. So this is the integration. So the function, what should I how should I write the function? So this readily we can see that, okay, when I integrate from minus t by 2 t by 2, then from minus t by 2 to minus a by 2 it is 0, and then from a by 2 to t by 2 it is 0, right? So the basically this integration over a period is reduced to a simple integration in only the on time of the signal, right? So I can write it as this 1 by t, and the integration is modified to minus a by 2 to a by 2, because rest of the region it is 0, right? So if you want, I can write it, but I don't want to. So if you write it like this, if you break it down, so you will do minus t by 2 to minus a by 2. What is the function value fpt? It is 0 multiplied by something dt. I am not writing that something, okay, plus then you write minus a by 2 to a by 2, and you write as, what is the value of the signal in minus a by 2 to a by 2, it is plus v, right? So you write v multiplied by something dt, and then the third integration would be a by 2 to t by 2, and then again 0 multiplied by something dt, right? So now we readily see that these two things, this is 0 multiplied by something and 0 multiplied by something, they turn out to be 0. The only integration that we have to do is this one here, right? So let us, why not write it clearly over here? So this integration is minus a by 2 to a by 2 v, which is a constant, multiplied by e power minus j n omega naught t dt. I'll request you to do this integration by yourself, even if I do it now, because this is one integration that will, and one result that will come repeating time and again and time and again, okay? So this integration, if we do the integration, it is simple, e power j theta, right? So if we integrate e power j theta, it turns out to be e power j theta. We put the limit, and the result end result, I'm not only going to write the end result, not writing the, okay, or we can write it even, no problem. So v will go outside, and then multiplied by, if I directly put the limits, then what it should be, it should be e power j n omega naught j n omega naught a by 2 minus e power minus j n omega naught a by 2, sorry, a by 2, and then you divide it by twice j, I have done this before, so I'm writing the result directly, and if you simplify this, I'll write the end result. End result is more interesting here and more significant also. So our end CN ripple that we wanted turns out to be V naught or V. This is the voltage of the on time, voltage of the signal at one on time, and then A by capital T, where A is your on duration and T is your total time period, right? And then this two exponential, they are added up to give you a sine n omega naught A by 2, and then you divide it by n omega naught A by 2. Okay, so this is my so these are my complex exponential Fourier series coefficients, right? So what is the significance of this? What am I why am I all of a sudden doing such a known problem? You'll see why we are doing this known problem. Why we are taking this particular example is also not insignificant. Let's see. Let's move it up. Okay, so now we understand that if we try and solve this, then we are going to find the Fourier series coefficients to be like this. Now suppose I make a small change, and what I do is I keep my A fixed. Okay, what if I keep my A fixed and keep on increasing the time period? Okay, I'll repeat again. What if I keep my A fixed, so I keep the on time fixed and then keep on increasing my time period? So essentially what we are doing, we are calling our A by T as, we are calling our A by T by one number, and then changing that number. Okay, uh, let's see what happens then. So basically what is happening is this. So in the next plot, if I keep my A fixed and I increase my time period T, how would the plot look? So the on time is fixed, so the signal in this small region minus A by T to minus A by 2 to A by 2, it remains essentially same, right? Nothing happens to it because I have kept A fixed, but I have increased T. So what will happen? So this T by 2 will turn out to be here, and then the next signal will start from even further a point, right? So you see, the only thing that I have changed, or that I am going to change, is I am increasing the distance between the repetitions of the signal. So I'm increasing the time period, but I'm keeping the on time fixed. That is a very critical point, that we have to keep the on time fixed, right? So we are keeping the on time fixed and increasing the time period of the signal, and we hope to discover what happens then. Okay, so what is supposed to happen? It is very simple thing that might happen, that not very many things can happen. It is like this. So if I plotted the spectrum now, what am I supposed to find? Like we said just now, that we are going to, maybe depending on the symmetry, we are not going to get into the details of it, maybe we'll get a DC, and then we'll get some bunch of terms at, what are the frequencies, at what frequencies will I get those terms? At maybe omega naught, which is my fundamental, maybe at twice omega naught. So these are my possibilities, and then 3 omega naught, right? Then 4 omega naught. These are my possible frequencies, 5 and 6 and 7 and 8 and so on and so forth. Maybe this at omega naught it would be some value, maybe at 2 omega naught it be 0, maybe at 3 omega naught it have some value. That would depend on how this sine x by x thing looks. Well, all of you know that this sine x by x, which is also called a sinc function, the sinc function looks something like this. Its envelope has a nature like this. If you don't take the magnitude, then it, oscillates and converges, oscillates and converges. So it has a nature like this. The sinc function has a nature, of course the same on the other side. So now, so you understand that we have, let me remove it so we are clear. Okay, so now we understand that we expect to have our spectrum at discrete frequencies. What are those frequencies? They would be omega naught, and then twice omega naught. Of course there is a 0 first, and so on and so forth, n omega naught, and then there might be a n plus 1 omega naught. This way it will go up to infinity unless it converges before that. So now if I ask, what is the distance between two spectral lines? What are the spectral lines? These are the things we are plotting in the spectrum of the Fourier series, right? So it could be a one impulse at omega naught, then one at twice omega naught, then one at 3 omega naught, so on and so forth. So what is the spectral gap between two lines? Can we find out what is the spectral gap between the two lines? I can take any two lines and get the difference between them. So if I take the n plus 1th harmonic and the nth harmonic, take a difference between them and try to find the spectral gap, then what do I find? N plus omega naught minus n omega naught. So it will turn out to be, one moment, n plus 1 omega naught minus n omega naught. So what we have is essentially omega naught, right? So omega naught is nothing but 2 pi by t. We all know this, that omega naught is nothing but 2 pi by t, right? Now you see, now we'll come to the point that omega naught is nothing but 2 pi by t, but here we said that a by t, this quantity, we are going to write as 1 by n, where n is the number that we wanted to vary, right? If we keep a fixed and keep on increasing the time period t like we said, then we are doing nothing but basically increasing n. We are increasing n indefinitely, right? So if I put this a by t equal to n, then what will I have? That this delta omega, or the distance between the two spectral lines turns out to be how much? 2 pi divided by, in place of t I can write a into n, right? Because a was fixed and n was something that we were varying. Now you see the most interesting result here. What does this mean? It means that because your a is fixed, this 2 pi is a fixed quantity, the only thing that I am increasing or keep on increasing is this n. So what happens if I keep on increasing this n? The delta omega becomes smaller and smaller and smaller, right? So if I, what does it mean in terms of the signal then? It means that if you keep on increasing n, you repeat your signal. Suppose this signal, it was repeated here, then the next one would be repeat after some distance even further. Then the next one, if I keep on increasing n, your next pulse will be repeated at a even later time. So if you keep on increasing this n in our formula, what we are essentially doing is to keep the repetitions far apart. What happens, it becomes when n becomes infinitely large? That's what we are going to observe later on. But for now, you see, let's speculate, or not speculate really, we'll see in MATLAB shortly. But what should happen? My n equal to, the spectral gaps, the distance between the two spectral lines, in terms of the integer values, they are still same. I still have a omega naught and then twice omega naught. But this omega naught and twice omega naught, because both of them have changed, the distance between them, the two, has become smaller, right? If this is for n equal to say half, then for n equal to say 1/5, you will have a spectrum like this. You see, there might be one line here, then in between also there will be lines. So there will be more number of lines in the same frequency range. Now if you make n equal to 1 by 10, then you will have even more number of lines in the same frequency range. Sorry, you will have more number of lines. So there will be one here, one here, one here, one here, like this, right? So your number of spectral lines will keep on increasing as you increase your n. Why is this happening? Because we saw that, okay, the distance between the two spectral lines is actually dependent on the n, right, or a by t. So if I keep a fixed and keep on increasing the time period, we are essentially increasing a by t, and we are essentially decreasing a by t and increasing n, right? And the result is simple. Result is that the spectral lines become closely spaced, one. And the other point that we cannot skip is that the spectral magnitude. What happens to the magnitude? We are talking about the spectral gap, the distance between, or the gap between two spectral components becomes smaller. So more and more number of harmonics are now packed within the same frequency range. Fine, but at the same time, if you observe that my spectrum magnitude is also decreasing, because a by t is in the magnitude. So if you keep on increasing your time period, your a by t is decreasing. So the magnitude. So we have two observations. First observation is magnitude decreases. As n increases, your magnitude decreases, spectral magnitude decreases. Number two is spectral gap also decreases, right? So these are the two very important major observations that we make through this example. Now what we are going to do, we are going to see mathematically what should happen or what happens when we let this time period becomes close to infinity. What happens when t tends to infinity? First, let's see why are we at all interested in t, letting t tending to infinity. What's the significance of that, or why is it necessary? So if you have a signal like this, like we plotted in the last screen, and then we say that okay, this is going to repeat after time t, let's say like this. So let's say this to be t by 2 and this to be t. So if it repeats after the time t, then if I keep on increasing the time period, what will happen? So if I'll draw two pictures. The next picture will be a little bit larger time period. So the first one was here, sorry. So the first one was here, and the next one will, now if I make t larger, the next one might be repeated after a later interval. What happens when I make t tends to infinity now? So what does it mean, making t tends to? So we are trying to see what is the physical meaning of t tending to infinity, or the time period of a periodic signal becoming close to infinity. What does it mean? It means that okay, your first pulse will be here, no issues with that, but the next one will be repeated after a infinite time. So what does it mean? That if I say that something repeats after infinite time, it is same as saying that it is never repeated, right? So it is never repeated, it is never repeated, or in other words, it will become an aperiodic signal. Aperiodic signal. So it becomes an aperiodic signal. So from, if you start with your periodic signal with a time period of t, and if you let t tends to infinity, you are essentially dealing with now aperiodic signals which are never repeated, right? So why are these important? Because you see, practically in any physical quantities, if you see any physical signals, if you observe, none of them are ideally periodic, right? Because periodic signals, by virtue of their definition, they need to continue for infinite time. It should repeat and repeat after every t intervals, so it should never end. But practical signals, they are seldom like that, right? So any signal, if you try to observe, suppose solar bursts or some radio signals coming from any astronomical figures or some place, anything, those are of finite duration, right? So any signal that is of finite duration cannot be a periodic signal. So we need to have the tools that are necessary to analyze this, these aperiodic signals. So that's what we are going to do. We are going to take our Fourier series understanding, and then we are going to let the time period become infinitely large, so that we can use our Fourier series tools to find out what to do or how to deal with these new aperiodic signals. Okay, let's see how to do that. So to do that, first off, we are going to again start with a periodic signal. Let it be an arbitrary periodic signal, whatever it is, that repeats itself after certain interval. Okay, so this is a periodic signal of ours, we call it ft or whatever, and then let it repeat after some interval or some t, say. Okay, so now we know from our Fourier series understanding that the Fourier series coefficient I can calculate for any periodic signal using our formula 1 by t, and then integrate it from minus t by 2 to t by 2, right? And then we say that okay, I am going to integrate from ft e power minus j n omega naught t dt, right? If you integrate this, then we are able to find out this Cn ripple, right? So what if I wish to take this t here to the other side, see what happens. So Cn ripple multiplied by t turns out to be minus t by 2 to t by 2, and then the rest of the things remain same. Ft e power j omega t j n omega naught t dt, right? So this is nothing but I simply multiplied the time on the took the time on the other side, and now if can I write it like this, I call this Cn ripple into t, I call this j n omega naught, because it is going to be a function of n omega naught, because on the right hand side you see we are doing the integration in terms of time. So what we are going to be left with is n omega naught, or function of n omega naught. So this f and j n omega naught, I call it as Cn ripple multiplied by t, or we can write it, see if we can write it like this t, can I write it as 2 pi by omega naught, right? Because we know that time period is nothing but twice pi by omega naught, right? Now in the last slide, or I should not say slide, last screen, we saw that we know that for a periodic signal, if one harmonic is placed at n omega naught, then the next one will obviously be placed at n plus 1 omega naught, right? So these omega naught, what is the difference between the spectral gap? We calculated that spectral gap to be, again I'll write it, let's n plus omega 1 omega naught minus n omega naught, and this was equal to omega naught, right? So omega naught was essentially equal to the spectral gap, right? So if I put it over here, let's see what happens. Cn ripple multiplied by twice pi divided by delta omega. So here in this case, our this delta omega is the spectral gap, right? So if I simplify to write Cn ripple as, how should I write it? Okay, f j n omega naught multiplied by delta omega by 2 pi, right? So this is nothing new. We have simply, you could say that made it in a different form, because this is in this f and f j and omega, the same integration lies, right? But we are denoting it in a different form. Okay, great. So now that we know how Cn j omega looks, maybe we can go back to our Fourier series. Maybe we can go back to our Fourier series and write the function itself, right? So if this was ft, then why not write the Fourier series for the function itself? We know that the Fourier series, the definition would be sum over n, I'm not writing minus infinity to infinity, and then it should be Cn ripple, if those are the coefficient, then multiplied by e power j n omega naught t, right? This is the Fourier series. Now what we are going to do, we are going to simply write it as n, then in place of Cn ripple I am going to put all these things. How should I write? F j n omega naught into delta omega by 2 pi multiplied by e power minus, sorry, not minus, e power j n omega naught t, right? Now you see is the trick. Now we are going to play the trick. What is the trick? The trick is very simple. Let us find out what happens when we take the limit t tends to infinity, because that's what we were interested in, right? That's when my periodic signal would become aperiodic, right? If we want to find out the Fourier analysis for this signal only, so we start saying that okay, although we have this aperiodic signal, let it be periodic, let it repeat itself after time t, and then we call that time period t tending to be infinity, so that it essentially played a trick by making the aperiodic signal look like periodic, and then saying that okay, the period is infinity. Okay, so that's what we are going to do. So if we put I'm not sorry, let me put the limit over here only. What if we put the limit time period t tending to infinity over here only? Then what change should I make? If you look carefully, if your time tends to infinity, then what happens to the omega naught? Because omega naught is 2 pi by t, right? And we know that delta omega is almost or actually equal to omega naught. So we know from the first principle of integration that this essentially, there are two major changes. First one, that n omega naught, or in place of omega naught if I write delta omega, so this turns out to be n delta omega, this turns out to be n delta omega, right? So we know that n delta omega or n omega naught, our n omega naught would turn out to be omega continuous variable, because omega naught has become very small as the time period increased, and our delta omega would turn out to be d omega, right? These are the two changes that I have to anticipate, and if we do make these two changes, then what happens to my formula? It turns out to be simply ft, let me use a different color. It turns out to be ft equals that 1 by 2 pi I could do nothing with, so that remains 1 by 2 pi. Then this limit is from first principle of integration, this turned out to be a integration instead of a summation. The limit goes from minus infinity to infinity, right? And then inside this it turned out to be f of, instead of j n omega naught, which were discrete variables, it turned out to be j omega, which is a continuous variable, which was also logical from our understanding that okay, even if that was happening and our spectral gap was becoming smaller and smaller, so no point in having discrete harmonics, because we are not going to have discrete harmonics anymore. We are going to have continuous, so closely spaced spectral components that they would eventually look like a continuous function, right? So f j omega, and this e power j omega t, e power j omega t, because here also this n omega naught became the continuous variable omega, and this delta omega, it turned out to be d omega. So instead of having the nice summation form of the Fourier series, we are now have we now have the continuous time integral form of the Fourier analysis, right? So this is what uh, a periodic signal or an arbitrary signal look like if I tried to represent them in the Fourier form or the complex exponential form here also now. But you see, it was logical, but let's try to have a feel physically that this is understandable and logical. You see, now if I go back go back to our very basic understanding of any transformation, what did we say? We said that what we are trying to do is nothing but represent our original signal in terms of some standards, right? So in case of Fourier series, because our original signal was periodic, those standards, only a certain number of discrete standards I had to take. I could add them up, multiply them, scale them, and do a linear combination. That way I could generate my periodic signal. But now my function itself has become aperiodic, right? That I want to represent ft, it has become aperiodic, but the functions that I am using, those are which functions? These are the functions, these are the kernels. These periodic or aperiodic? These are all periodic functions, right? Because we know that the complex exponential e power j omega t is a periodic signal by nature. So if I try to use bunch of periodic signals, add them up, scale them up to generate an aperiodic signal, so how many terms do I need? Of course we are going to need so very many number of terms, and there would be continuously many number of terms, right? Because we are using periodic signals or periodic kernels to create aperiodic signals. So there of course I need infinitely many number of terms, and infinitely many number of terms in a fixed frequency range also, which makes the spectrum continuous, because the gap between the two adjacent spectrum has become smaller and smaller now, right? But I'll just touch upon this, you'll study it later, that if you somehow can change this kernel, if you can somehow say that okay, why not use aperiodic standards for aperiodic signals. And why not use periodic standards to generate periodic signals? That is also valid, because there are many transformation techniques where the basis or the standard set of functions or signals, they are by themselves aperiodic in nature, like pulses or Haar wavelets, or those are called wavelets. Let's not go into that. But why, if you use aperiodic standards to generate aperiodic, of course you will need lesser number of terms. Then there you won't need this, infinite sum or this infinite integration. But here, in case of Fourier analysis, whether you are in Fourier series or in Fourier transform, particularly in Fourier transform, because you are trying to use periodic signals to generate a periodic signal, which is our ft, then you will need infinitely many number of terms, and the gap between two adjacent spectrum will become smaller and smaller, and it will turn out to be a continuous thing, right? Okay, so we are going to talk up to this point only. Let's go into the actual formula and all, and how to do different problems. Let's go into them in our next class. But before we stop, I would like to just show what we discussed in MATLAB. Let's see if we can do that. Okay, so this is the same code that I shared with you day before, and I mean last week, and it is, we are going to see the exact same signal that we just plotted in paint and that we took the reference of. So the signal was on for some time, then off for some time, right? So I'll make it simple. So I'll say that, okay, if my time is less than or equal some a, then something should happen, else something else should happen. So if it is less than a, then what should happen? Then of course my signal should be a plus v, otherwise my signal should be 0, right? This is as simple as that. Great. So if I plot it, let's see if we did it correctly. Let's see it once. If we did it correctly, then we'll move on. Sorry. Okay, here. Oh, I'm sorry, I took it. Now it will be fine. Okay, now it is correct. So I have taken a 0.005, so 50% duty cycle, so on and then off. Okay, and what we are going to do, we are going to change the time period without changing the, you see, without changing the on time. So on time I'll keep fixed at 0.005 seconds, and the time period I'm going to change continuously. I'll take 3 cases or 4 cases, and we are going to make observations on what happens to the Fourier series coefficients, right? We are calculating the Fourier series, and we wish to observe what happens when I keep the on time fixed, but change the overall time period of the signal, like we said from the very beginning. Okay, okay, let me stop this plot here, and if you look at the coefficient calculation, it is same as before. I'm not going to, I don't think I need to explain it. Okay, let's run it. Okay, so this is the coefficients up to 5 kilohertz, you can see, and these are the coefficients. Fine, these we understand, right? So let me just x limit so that we can visualize it better, from 0 to 5000, right? So we can see, let's hold it on. Now see, the time period was 0.01 seconds, on time was half of that. Now I am going to make the time period a little bit larger. Let's see what happens. Change the color, plot it, see what has happened. It's funny because I have kept the number of harmonics fixed, so the frequency range obviously will change, right? Because it will start from minus n omega naught to n omega naught. If your omega naught has by itself become smaller, so obviously you need more number of terms to compute. But let's see what happened inside this 0 to 1000 kilohertz or 1000. Now do you see what has happened? Firstly, you see the blue one was 0.01 seconds, right? And the black one is 0.05 seconds. So I have increased the time period by 5 times. So what has happened, you see, the amplitude has reduced by 5 times, and you see before the distance between two adjacent spectrum was this much, right? If you can see. Now look at the black plot. The distance between two adjacent spectrum has become 1/5 of that, right? Now see what happens if I keep it increasing and make it say 0.1. I'm not sure whether we'll be able to see it, but let's try. Plot it. Do you see what has happened? Now let's let's restrict the range from 0 to 100 or 200 maybe, I think. Yeah, now you see what has happened. Previously you have this, first you see the magnitude has become even smaller, right? And you see before you had, uh, for the first case for 0.01 seconds you had the spectral gap this much. Now look at the black one, you had the distance this much. Now look at the red one, you have the distance this much. So if this way you keep on increasing the time period of the signal, your amplitude will become smaller and smaller and smaller, and you will have more and more and more number of spectral points in the same frequency range. Now if you make this t equal to 1, I don't know what will happen, but what is there not to try? Can you see? Great. If we restrict it within 50, maybe we can see. And also if we y limit from say 0 to 0.1 maybe. Now do you see the green one? I have made it 10 times. So in this, even this, the red ones, between the red ones there are so many spectral components that has come up, right? So this way if you keep on increasing your time period, if you bring it toward infinity, there will be so very many number of samples so closely spaced together, it will look like a continuous envelope. That's what happened in the math also, that the discrete spectrum with n omega naught became omega, right? So the discrete spectrum of n omega naught, where the fundamental was omega naught, then 2 omega naught, 3 omega naught, so on and so forth, it turned out to be a continuous variable omega. That is a very significant thing. Okay, we are going to talk about that in our next class, but I hope you understood, and you can try this code by yourself also to see what is what. Okay, so thank you, and let's see in our next class. Thank you.